All right then. Okay, so thank you everyone for coming. And it's been some lot for José Miguel. So I'll let José Miguel maybe to a bit more, but basically José Miguel, he's been doing research similar to what we've seen. I mean, all in data optimization. He's also done some research on reinforcement learning, right? A lot of these things apply to the clinical phase. Some of his papers were one of the ones that I've read a lot, particularly with the past. They were my good time reading some of the papers, so I'm very, very glad that he accepted the invitation.
Good. Thanks a lot for inviting me to give this talk today. I can say a few words about me. I'm one of the PIs or leaders in the machine learning group here in Cambridge. I did my undergrad and PhD in Madrid, in Universidad Autónoma of Madrid. And then I came to Cambridge for a postdoc. I was working with Subin Garamani, who is kind of very well known in Bayesian, in the area of Bayesian machine learning. And then I moved to Harvard for a postdoc. I was working with Brian Adams, who is very well known in Bayesian optimization. And then after Harvard, I came back here and took a faculty position and started my group. I have about 8, 9 PhD students, a couple of postdocs, and I work quite a lot on Bayesian methods. Most of my work in machine learning has a strong focus on Bayesian methodology. I care a lot about uncertainties. And I also care about combining Bayesian methods with deep learning. We're going to see this in this talk. We're going to see combinations of Bayesian methods like Gaussian processes and deep neural networks. And I care about using the uncertainties that Bayesian methods provide to solve practical problems. And we're going to see that Bayesian optimization, which is some problem that we're going to be looking at, uses a lot of uncertainties. And uncertainties are extremely useful in Bayesian optimization to solve efficiently this type of optimization problems that we want to solve. So yeah, I'm very excited about the intersection of Bayesian methods and deep learning and applications like in Bayesian optimization and in real-world settings such as in molecular property prediction and molecular optimization, which is what we are going to be looking at. Does this work? It's frozen. It was working just 1 second ago. Okay. Okay, now it works. Good. So what I'm going to present here is some work that has been accepted at ICLR. And I think sorry, it was at NeurIPS. No, it's ICLR. Yeah, it's ICLR, and this is going to be presented in a few months in ICLR, which is taking place in Atlanta this year. This was mainly done by 2 of my PhD students, Wenli Chen and Austin Tripp, and they deserve all the credit, most of the credit of what I'm going to present here. Good. What is the problem that we're going to try to solve? We want to find new molecules with improved properties. And this is an extremely important problem because almost everything that is around us is made of molecules. And molecules can have very useful applications. We may want to design new drugs that are more effective for treating new diseases. Maybe we want to design a new antiviral for COVID, for example, or for another disease. We may want to find new molecules to build materials with important properties, for example, organic photovoltaics. Most of the phones, TVs, they have now, they're built using LEDs, and they're made of organic materials. And you may want to find new materials that maybe have better properties for building these devices. You may also want to produce more efficient energy from the light of the sun. You may want to find new organic photovoltaics that have better power conversion efficiency, and so on. I mean, there are tons of applications. So this is an exciting problem, but it's extremely challenging as well. And the reason it's extremely challenging is that if you have a candidate molecule, evaluating the properties of this molecule is usually very slow and expensive. You may have a candidate molecule. This is, for example, a virtual molecule that has not been created yet. You may have to synthesize the molecule. You may obtain some compounds, and then you have to validate those compounds in practice. Maybe you have to do experiments to see how effective a particular drug is, or maybe you have to do also experiments to see if your organic photovoltaic is having the right properties or not. And this is extremely expensive. It requires a lot of labor to do this. The other problem is that chemical space is huge. If you think about the possible number of molecules, it's a huge number. And this is a massive space. And what is going to happen is that the few molecules that have useful properties are small. There are only a few molecules that maybe are relevant for your problem. And the space, chemical space is huge. And finding the few molecules that have important and interesting properties among the many irrelevant ones is going to be very time consuming. You want to accelerate this search for new molecules. And what you can use is use efficient methods, data-driven methods to speed up this search. And that's where we're going to be using Bayesian optimization techniques to accelerate the search for new molecules with improved properties. That's great. Bayesian optimization has been applied in many settings. We're going to be using here Bayesian optimization. And one of the key things when you implement Bayesian optimization in practice is that the performance, obviously the most critical factor probably, probably you have heard about Bayesian optimization, you have all these fancy acquisition functions. And I think you saw recently some about the information theoretic acquisition functions. I have worked a lot in that area. I have come up with my own acquisition functions and all that. In Bayesian optimization, if you implement it in practice, you may say, oh, I want to implement Bayesian optimization. Should I use this acquisition function? The other one is going to be make a big difference. The most important factor for the good empirical performance of Bayesian optimization is the quality of your predictions. It doesn't matter much. You can use one acquisition function or another. If your predictions are very, very good, that's what is going to make a huge difference. And obviously, what is going to happen is that at the beginning of the optimization process, you don't have much data. No, you have collected only a few data points. And that's where your predictions are going to be worse. You don't have much data, and you have more data, your predictions improve. If you want to improve the performance of Bayesian optimization, you should try to improve your predictive performance when you don't have much data. So the performance of Bayesian optimization depends a lot on how well you can predict these properties from data. And at the beginning, you don't have much data, and you want to improve your predictions in that setting. What we're going to see here is a collection of techniques that will allow us to improve the predictive performance when you don't have a lot of data points. And this is usually called, in the machine learning literature, usually called this setting few-shot learning. Few-shot learning, it means that you want to make predictions with a very small number of data points. Some people have addressed the few-shot learning problem where you maybe only have one example, one data point, or maybe 5 data points. You are in a very low data regime, and you want to make very good predictions in that setting. And what we are going to see here is a collection of few-shot learning methods that are going to be used to predict the properties of molecules. Few-shot learning has been widely used in computer vision. In many problems where you have, for example, I think this is the area where few-shot learning was proposed initially. You have images, maybe of characters. Someone tells you this is a new character, maybe a fancy character that you make up. And then you have to learn to recognize that character. And you need to do it maybe from only one example of that character. That's the few-shot learning setting. People have applied few-shot learning methods a lot in image recognition problems. And here we're going to do it in the molecular property prediction setting, which is slightly different. Good. So let's have a look at Bayesian optimization. I think you've had some review of this by Henry recently. I'm going to give like a brief summary. And one of the key things that I'm going to show here is why uncertainty is very important in Bayesian optimization, which is another of the things that I mentioned. So imagine this is now your space of molecules. This horizontal axis is chemical space, and you may want to find now a molecule with improved properties. And the properties of the molecule maybe is represented in a, I mean, this is an idealized setting, obviously. The objective function could be this one. Maybe it tells you the properties that the molecules have, and you may want to minimize this. So you want to find the molecule that achieves maybe the lowest value of your objective. This is an idealized setting, obviously. In practice, what is going to happen is that this space is high dimensional and this objective is very complicated and it's not going to be that smooth, of course, as this one. So good, we want to find now new molecules with improved properties. And this is the objective that we want to minimize. We don't have access to this objective. We only have access to data that we can collect. We can synthesize some molecules, evaluate them, and get some estimate of their property. And this could be, for example, some data points that we obtain. That's all we have to make decisions. And now we want to decide maybe what molecules we should try next to evaluate based on this data. And Bayesian optimization methods, the way they work is that you combine two elements. One is going to be a prediction model. You are going to feed a predictive model to this data, and you are going to make predictions about the possible objective values for new molecules. Now, in new inputs here, for which I don't have data, and I want to make predictions about the objective. And typically, you will use a Gaussian process model. This is kind of the default model in Bayesian optimization. The Gaussian process is a probability distribution over functions, and this shows potential functions that could have generated this data. Obviously, where you have data, the uncertainty is low, and where you don't have data, there is a higher uncertainty because you don't have any data. Good. So we have this model. We can summarize now the predictions by the mean and the standard deviation. This is typically the plots that you have when you show the predictive distribution of a Gaussian process. Now, this is one of the components of any Bayesian optimization method, a predictive model. The other component is going to be a data collection strategy. Basically, given the predictions of my model, I want to collect data next. How should I collect this data? And there are many different strategies to collect data. Typically, these strategies work by specifying a particular utility. You have this utility function that tells you how useful it is to collect the data point y, the output y, at the input x, given the data that I have collected so far. There are many different utility functions. You probably have heard about the expected improvement, entropy search, probability of improvement. I know, there are like tons of things. Expected improvement is one widely used, and this utility is just the improvement. How much you improve over your maybe best values in so far. The output of this, the expected utility, is the acquisition function that tells you how useful it is to collect data at each point. This acquisition function is obtained from the predictions of the model. No? You just use your model to predict the utility, the expected utility. And the key thing is that now evaluating this acquisition function is extremely fast compared to evaluating the objective, no? Because this is just done in your computer, and you can just evaluate it very fast. The acquisition function is telling you where you should collect data next. No? And typically, you are going to maximize this acquisition function to choose the next evaluation location. And here you can find how Bayesian optimization methods, they trade off exploration and exploitation. Ideally, because you want to minimize the objective, your acquisition function is going to tell you collect data where the objective on average takes low values because you want to minimize. No? So you see that in this region, the objective takes low values, and that's why the acquisition function is high. The acquisition function also cares about exploration. It's useless to collect data where you already know the value of the objective. And you can see that in the regions where you already have data points, the value of the acquisition function is very low. It's useless to collect data close to where you already have. And that's how the acquisition function in the end is going to balance exploration and exploitation in this way. It's going to find, it's going to favor the collection of data at points where, on average, the objective takes low values, but also where your uncertainty is high. And that's why in this region here, although the objective takes low values, because you already have data in this region, it's less useful to collect data in that part of the space. And that's why the acquisition function is favoring the collection of data there. So you can then optimize your acquisition function numerically in your computer. You typically use an optimization method for this. There are tons of things to try. You find this input that maximizes your acquisition function. Even if you don't optimize the acquisition function globally, you may still do well. Even if the next point that you are collecting is not the optima of the acquisition function, Bayesian optimization methods still work fine. So then you collect data at this location, you update the predictions of your model, and then you repeat the process. You get a new updated prediction. This point was actually really bad in terms of the objective. And now you recompute your acquisition function, and here you say, okay, don't collect the data anymore there. It's not good. Let's focus somewhere else. And then you focus in this region because actually here you take low values and there is high uncertainty. You collect data there, and then you repeat the process. And typically you will be repeating this process until you run out of some budget for collecting data. You repeat the process, and you can see how this is collecting data in an efficient way. And now this is the interesting thing, in this plot. You can look at the prediction of the Gaussian process model. The mean of the prediction is shown in blue. And what happens here is that in this central region, on average, I'm getting worse things than what I have obtained before. No? This is worse than these points or these points. So if I don't look at the uncertainty, I wouldn't really care much about this region because my model is saying this is going to be worse than in other regions. So if you look only at the predicted mean, you will be collecting data maybe in this region or in this region, but not here. The problem is, I mean, what happens in practice is that you don't have data in that region and your uncertainty is quite high. And now the acquisition function is focusing on exploring. You already have a lot of data in other regions. Here you don't have a lot of data. And it's going to be useful now to explore. And because maybe there is a chance that you will get something better here. No? You can see it from the confidence bands. Here, there is a chance that you may get actually points that are better than those. Yeah. And actually, when you collect data in this point, you are able to find better solutions. And this illustrates why using uncertainty is quite useful in Bayesian optimization. It will allow you to achieve better solutions than if you don't use uncertainties. And that's why following Bayesian approaches is the right thing to do when you try to solve these problems. Good. Any questions so far on this, or everyone is quite familiar with this already? Yes, okay. Yeah. Good. So this sounds great. Bayesian optimization method is an amazing method. However, performance is highly dependent on the quality of your predictions. This is the most important factor in Bayesian optimization, how good your predictions are. At the beginning of your optimization, you have very few data points available to make predictions. Your predictions are going to be quite poor in that regime. And if you want to improve your performance, you probably want to improve the predictive performance when you don't have much data. What I'm going to present here is a method based on few-shot learning techniques that will be aiming at making very accurate predictions when you don't have a lot of data. And here I'm going to present a state-of-the-art method for few-shot learning when you want to optimize molecules, when you want to make predictions on the properties. Good. So few-shot learning, what is this? Let's have a look at the first convention and how you usually apply machine learning methods in practice. You may have this is using examples from the computer vision domain. Here you want to classify images. In our case, we don't want to classify images. We want to predict probabilities of molecules, but the problem is more or less very similar. So imagine that you have this conventional learning problem. You have this training set, and in this problem, you want to classify images of ducks, dolphins, and seagulls. Images are high-dimensional. Molecules are also relatively high-dimensional. And the predictive models that you need to make accurate predictions with images are really, really complicated. If you want to make very accurate predictions with images, you need very big neural networks that have lots of parameters. Here you have a training set with only 6 images. And you may have to, if you want to make accurate predictions, you may have to tune tons of parameters in a neural network. Obviously, if you want to make accurate predictions on this test set with new images that you haven't seen before, this approach is not going to work. There is no way you will be able to make accurate predictions in this setting with this high-dimensional data with only 6 data points, because you will need like very complicated models. So this doesn't work in a few-shot learning setting, and you need additional methodology to obtain gains. One approach that works quite well is to follow a meta-learning approach in this setting. And the idea is that, okay, you want to solve this problem, making predictions with these 6 images, and this is kind of the problem that you care about. We're going to call this the test task. This is the test task, is the task that you want to solve. You are given a particular training set for this task, and you want to make predictions on a test set for that task. In a meta-learning setting, this training and evaluation or test set, they are called support set and query set. You have a support set, which is kind of the training data, and the query set is like the set on which you want to make predictions and where you want your method to make accurate predictions. Now, you want to solve these tasks, but actually, maybe you have similar tasks that are about different prediction problems. For example, predicting if the image is a kitten, a lamb, or a boar, or a dog, shark, or lion. These are different prediction problems, but they are somehow related. And what can happen is that maybe you have many prediction problems, each one with a small number of data points, but maybe the methodology that you need to solve those problems is kind of similar. This is an example in the computer vision setting, but in molecules, you have the same setting as well. You may have many pharmaceutical companies that they have been collecting data about different tasks. Maybe they want to design a new drug, or so they have many different data sets. Most of these data sets, they have a small number of molecules. But if you think about it, then the methodology that you need to use to make predictions in those data sets is going to be similar. You will need to have, for example, a neural network that has many parameters and that receives your molecules as input, and then you want to make a prediction as an output. So the setting is similar in the case of the molecules, and here we're looking at how it is with images just because this is helpful to us. Now, you are going to exploit these additional learning tasks or data sets, additional data sets that are related to each other. And the idea of how meta-learning works is as follows. A meta-learning method, actually it's called meta-learning because it's kind of what you typically do in machine learning, but maybe one step above that. So in machine learning, you have your training set. You have a machine learning method that processes the training set. This will involve maybe optimizing your weights. You fine-tune your method on the training set. And then once you have done that, you evaluate how well your method makes predictions on validation data. I'm going to call it validation data, or it could be your test set, but I'm going to just use validation data. So that's the process that you are typically doing in machine learning. You process your training set and you evaluate performance on the validation data. And you want your validation data obviously to be as high as possible. Now, think about putting another learning process on top of that, where you can now fine-tune things that affect the performance of your method. And you are now not going to optimize performance on the training set, but you're going to optimize performance on the validation data. So you have now like a two-level process. First, your method processes the training set. It makes predictions on the validation data. You look at how well those predictions are on the validation data, and then you fine-tune your method. And that's where the meta-learning is happening. You are kind of learning, you are changing your training process so that the final prediction of the validation data is as good as possible. So there's like a two-level learning process. One learning when you process your training set, and another learning process when you maximize performance on the validation data. And that's what meta-learning methods do. So each meta-learning method is going to go to the data for each of these tasks. It's going to maybe take the data for a particular task and split the data into training and validation randomly. The meta-learning method is going to process the training set. Based on that, it's going to make predictions on the validation set for that task. And then you're going to optimize your meta-learning method to maximize performance on the validation data. So that's why there is this meta-learning approach where you have like the learning process one level above the typical learning process in machine learning. Good. So once you have done that, you have created a predictor that works well when you process the training set and you make predictions on the validation set on the tasks that you have been working with. Now you go to your test task. and you take your meta-learning method and say, oh, now I have another training set. I'm going to process this training set with my meta-learning method, and then I'm going to make the inference on this test set. And the key thing now is that although your training set has only 6 data points, your meta-learning method has been tuned to work well on maybe tons of data points or from many different tasks, each one maybe with a small number of training data points, like 6 in this case. But putting together all these data sets is a lot of data. Okay, that's kind of how meta-learning methods are going to work. Okay. Any questions on this? No? Good. So let's see how we can do this with molecules. This sounds good. The first thing that we need to do this is data. And it turns out that the researchers here at Microsoft Research Cambridge, they published a paper at the new abstract on benchmark problems. This paper is called FSMOL, and it's a few-shot learning dataset for molecules. This is an amazing dataset. It contains about 5,000 tasks. It has 5,000 tasks, each one with a small number of data points. Let me see. Yeah, maybe from 32 to 500 data points per task, but you have 5,000 tasks, which is a lot of data. And typically, each of these tasks is just you have a target protein and you want to know if a particular molecule is going to bind to the target protein or not. And obviously, the problems are different because the target protein is different for each of these problems. So you can think that each task is going to be more or less like this. You have like data set with different molecules like these ones, and then you have some properties. That is maybe the binding affinity of the molecule to the target. You can split these tasks into training tasks that you use to optimize your meta-learning method, validation tasks that you could use to validate the hyperparameters that you maybe have in your meta-learning method, and finally you have test tasks, which is the ones that you use for evaluating the performance. So it's a bit like what you normally do with data sets, where you split your data into subsets. But here, because you are doing meta-learning, now you have data sets of data sets. And you split your data sets of data sets into data sets that are for training, data sets that are for validation, and data sets that are for test performance. Good. So this is the data that we're going to be using. And now the question is, okay, that sounds great. We have now learned about meta-learning. How do meta-learning methods work? Do you have an example of a meta-learning method? And these researchers from Microsoft Research that put together this small data set, they took some few-shot learning methods from the computer vision setting, and then they tested them on the molecular setting. And then they found that actually some methods work very well in the case of molecules. And one of them was this prototypical networks. Prototypical networks is actually probably one of the simplest meta-learning methods, and it works as follows. You're going to have now your molecules, and what you're going to do is to use a neural network to find some feature representation of these molecules. This neural network could be something quite complicated. You could have graph neural networks. You could do something called molecular fingerprints, which is similar to a graph kernel, and then obtain a feature representation of the molecule using these molecular fingerprints, and then you could put a fully connected neural network that is going to transform that molecular fingerprint. In the end, you could have a combination of these things, but at the end, you just get like a feature vector representing your molecules. Then prototypical networks looks at these feature vectors encoding the molecules, and these are for classification because the FSMOL data sets are for classification. You take the binding affinity of the molecules in a data set and you just split it in half, and you just say the top 50% is class 1 and the bottom is class -1, and you just get like a binary classification. So you are solving a classification problem, and what you are going to do is to embed your molecules into this space using your neural networks, and then you are going to find some, once you embed the molecules into this space, you just do nearest centroid classification. And the idea is that you find the center of each class. So you embed the molecules of class 1, you embed the molecules of class -1, you compute the centroid for each of these clusters, and then you just do classification using nearest centroid. If you get a new molecule, the new molecule maybe is embedded into a vector that is maybe here, and then you just look at which is the centroid that is closest, is this one, so you predict that class. That's how probabilistic networks work. They work very well on the F-small data set, but they have limitations if you want to do Bayesian optimization with this method. First, this is a classification method, not a regression method, and we want to do regression if we want to do Bayesian optimization. The other thing is that this predictor is a nearest centroid classifier, and this is super simple. This may work well when you have only maybe 5 data points. But in Bayesian optimization, maybe we move into settings where you have maybe 10 data points, 20 data points, and then these decision boundaries are going to be too simple to make accurate predictions within the classification setting. The other thing is that this doesn't give you predictive uncertainty, and we have seen that predictive uncertainty is fundamental if you want to do Bayesian optimization. So what we are going to propose here is how to come up with a few-shot learning method that solves these limitations of prototypical networks. And the key thing is that we know that Gaussian processes are great for Bayesian optimization. We're going to take these ideas of prototypical networks that use this deep neural network as an encoder, and then we're going to combine this with Gaussian processes. One key thing, how does this thing fit into the few-shot learning or the meta-learning setting? The way the prototypical network works is that you process your, as I said, the meta-learning methods, they process the training set, and then you make predictions on the validation data, and then you optimize the performance of your method on the validation data. So the way you process your training set with this network is that you embed your data and you compute the centroids. And that's what is the processing of the training data. It involves computing your centroids. And then when you evaluate performance on the validation data, you just look at how well the new centroid classifier is doing. And how do you optimize this meta-learning method? You optimize the performance on the validation set, optimizing the weights of your neural network encoder. The only parameters of the meta-learning method is actually the weights of the neural network encoder, because the processing of the training data, the computation of these centroids is automatic. You don't have parameters there. There are no parameters in the computation of the centroids. It's just, I mean, maybe the parameters are the centroids. No, you just optimize them automatically by just finding the centroids. Good. So we are going to do something similar with Gaussian processes. And let's have a look at this. What we are going to do is use the same approach in the prototypical network to embed the data into some picture representation. And what we're going to do is to put a Gaussian process on top of that. And the result is a Gaussian process with something called a deep kernel. This has been used before in a slightly different setting, but the idea is that you have just your typical kernel or covariance function in a Gaussian process. This could be the squared exponential, your Gaussian covariance function. And what is going to happen is that the input to your Gaussian covariance function is going to be not the data X, it's going to be a transformation of the data to this neural network, which we call F. So this is nothing new. It's called deep kernel learning, has been proposed before. It was actually proposed by a PhD student from the Cambridge Machine Learning Group, Andrew Gordon-Wilson, some time ago. This thing never really worked very well. And the reason it never worked very well is because, I mean, the way it works is that you just optimize your Gaussian process, covariance function, hyperparameters, the length scale, the amplitudes, and all that, but you also optimize the weights of your neural network. And when you implement these methods in practice, all these nice properties of Gaussian processes that they are usually more robust to overfitting and all that, you lose those things. Your covariance function is not too complicated, and then you can severely overfit your training data. And that's why deep kernel learning has not been used much before. In this setting, we are not going to be affected by overfitting. And the reason is because of the meta-learning process. We're going to see how this works. Good. So maybe another view of how this method works. We have our neural network. It receives the molecules as inputs. And for each task, we get some feature representation of the molecules. The feature representation is given by this neural network that is shared across all the tasks. And now, given the Gaussian, the transformed representation of the molecules, we put a Gaussian process on top that representation, and we make predictions for each different task. And each Gaussian process for each task is different. It has its own bandwidth, length scale parameters, amplitude, and all that. And we're going to now optimize jointly the parameters of our neural network and the hyperparameters of our Gaussian processes on the different tasks. And the idea now is that we're going to jointly train these parameters. And we're going to do it in a meta-learning framework, in the sense that we're going to find now optimal neural network parameters such that when you use a Gaussian process on top of the transformed data by the neural network, and you do hyperparameter optimization on your Gaussian process, the resulting predictive performance of that Gaussian process on the validation data is as high as possible. So that's where the meta-learning thing is happening. It's happening because you are learning a neural network that is optimal for fitting a Gaussian process afterwards and making predictions with that Gaussian process. So the neural network weights have been tuned for that particular problem of fitting Gaussian processes on top of that representation. How do you do this in practice, and how does the meta-learning happen? It's shown here. The first step, imagine that you have some initial value for your neural network weights. You transform your training data for a particular task, and you tune Gaussian process hyperparameters. How do you tune Gaussian process hyperparameters? In the same way as you always do in Gaussian processes. You optimize the marginal likelihood. You optimize the probability that the Gaussian process gives to the training data. And that's what you have here. It's just a Gaussian density on the targets for the training data. As simple as that. Nothing new. Everyone has been training this Gaussian process in this way since ages. We just do the same. Now, you have already optimized your Gaussian process hyperparameters. This is what you do here in this operation. You have your training loss, is the Gaussian process marginal likelihood. You optimize it with respect to theta, and you get some optimal hyperparameters theta star. Now, what do you do next? You take your Gaussian process and you make predictions on the validation data. And the predictions of a Gaussian process on validation data is a multivariate Gaussian. So you have another multivariate Gaussian, which is shown here. And you look at this predictive probability given by this multivariate Gaussian on the validation data. And you just want to maximize that. You want that when your Gaussian process is used to make joint predictions on the validation data, what is the probability of observing these target values on the validation data jointly? So it's a multivariate Gaussian. I want to maximize that. And that's what you do in this outer optimization problem. You are going to your tasks. That's why you have this probability over tasks. You are looking at the validation data on that task. You are taking your optimal Gaussian process hyperparameters, and you use those to make predictions. Using as an encoder for the molecules with a neural network with these parameters theta. And what you are going to do is to optimize the neural network parameters. The neural network parameters phi. So phi are the neural network parameters. That's why you have these two nested optimization steps. One where you optimize the Gaussian process hyperparameters, and another one where you optimize the predictive performance of the Gaussian process with respect to the neural network weights. And that's what is giving you now a neural network that is tuned to make predictions with Gaussian processes. Good. Any question on this? No? Good. So how do you solve this problem? This is slightly different from the typical learning problems in machine learning. How do you do this? Using gradient-based optimization, as you always. You're going to use gradient-based tuning. This means, the Gaussian processes, hyperparameters, you just tune them in the same way as you always do. You take your LPFGS optimizer, second order methods. They are great for tuning hyperparameters. The number of hyperparameters usually is not very high dimensional. These LPFGS methods are great for them. You have already tuned your hyperparameters. You have your theta star value. And now you want to optimize your neural network weights. You need to look at the gradient of the validation loss or the performance of the validation data with respect to the neural network weights. And here is where the tricky thing happens. What happens now is that the gradient of the validation loss is going to depend on the direct contribution from the neural network weights, but it also depends on how the neural network weights are going to change your optimal Gaussian process hyperparameters theta star. And that's why you need now this gradient of the optimized Gaussian process hyperparameters with respect to the neural network weights. Because the neural network weights, if you change them, they're going to change how the data is encoded on the training set, and that's going to change how the hyperparameters, it's going to change the optimal Gaussian process hyperparameters. So what happens is that you can use this implicit function theorem, which actually gives you the exact gradient. You have already optimized your Gaussian process hyperparameters, you get theta star, and the gradient of theta star with respect to the neural network weights, you can show that it's the same as the inverse Hessian of your training loss with respect to the Gaussian process hyperparameters, times now this gradient of the training loss with respect to the Gaussian process hyperparameters, and then with respect to the neural network weights. This sounds a bit scary. In the end, it's actually very simple. You may find, okay, this is a fancy thing, implicit function theorem. There is this inverse Hessian. This looks a lot like Newton's method. Yeah? And you can actually derive this implicit function theorem in a super straightforward way just by differentiating the Newton step. If you are at some location and you do like a Newton step to get to the optima, and then you differentiate this optima that you obtain through the Newton step with respect to the neural network weights, you get this. So it's super easy to derive from Newton's step. Good. There is this inverse Hessian, which can be a bit scary. It's a Hessian, it's a matrix. People don't like Hessians with neural networks because usually these are huge matrices. Here, the Hessian is with respect to the Gaussian process hyperparameters. In a normal Gaussian process, you have length scale, amplitude, and noise. So it's 3 variables. This is a 3x3 matrix. We are not scared of this. This is another gradient of a gradient vector. This is 3-dimensional gradient vector, and then you need to compute the gradient of that gradient with respect to the neural network weights. So this is a matrix which is 3 by the number of neural network weights is still small. So that's fine. And that's all. That's all we need to do to get our gradients. We can do it very easily in this way. Good. Any questions on this? It's clear? Okay. Good. So let's see how this works in practice. This shows some results on this small data set. This is a plot that shows some improvement on this metric, the area under the persistent recall curve. This is classification. We are solving classification problems with Gaussian processes. And the way we do this is actually regressing the class labels. We do regression on 1 and -1. You may wonder, why do you do this? It works better than other things. That's why we do this. And tuning the GPs at the parameters is very easy in this way. So that's what we do. We also do regression on the targets before discretization to binary labels, and the results are similar. So hierarchy is better, and this on this axis we have now the support set size. This is the size of the training set on the test tasks. And what happens is that you have some tasks with more data and other tasks with less data. And what happens here is quite interesting. You have here the prototypical networks in green, and you see that as the amount of training data increases, prototypical networks actually don't improve fast, especially from going from 128 data points to 256, performance deteriorates. The reason for this is that they're using this nearest centroid classifier. It's a super simple classifier. The decision boundaries are all straight lines. And when you have a lot of data, your decision boundaries are probably with high confidence nonlinear. And that's why this method is not doing so great. So you want something more complicated. We see our method here in red, which actually improves significantly with the prototypical methods. We see how many different methods perform. You have here something called the random forest. You probably have heard about random forest. This is what pharmaceutical companies use by default when they make predictions on the properties of molecules. And we see that these methods random forest would be this method here. It's actually quite good. I mean, when we think of data, it's much better than many other methods. But our techniques are better. We compare with something called, single task. Really single task is here in gray. It's actually a bit similar to random forest. Use neighbor classifiers. There is something called MAT is a self-supervised learning method. And I don't know if you have heard about self-supervised learning. It's super trendy in computer vision settings because you can get very good performance with few data points. You just get some embedding of your data that is trained in this self-supervised learning method. And then when you have like labels, just we have to labels, you get very good performance. This doesn't work with molecules. With molecules, it seems to work less well. I think the problem is that your self-supervised learning methods, you encode a lot of prior knowledge about the data in the way you create your self-supervised tasks. And with images, you typically take crops of your image, maybe change the color, and then you try to see if two patches belong to the same image or to different images. These things may maybe work with images, but with molecular graphs, it's not clear how to design these self-supervised learning tasks. And that's why I think why this method doesn't work so well. This is for regression, and the results are more or less the same. We compare also with a method called DKT, which is multitask with Gaussian processes. And this method uses the same hyperparameters for all the tasks. And we see that it's worse than using different hyperparameters, as you would expect. Good. More results on something called molecule net, which is another benchmark. It's similar to FSmol, but it's a different benchmark. And we see that we do quite well in these problems. Toxcast, Move, and Tox21. In Tidal, we don't do so well, but it's only one of the cases. You cannot be the best on everything. This shows performance before using a pre-trained encoder. This data set is not so large, and then if you use a pre-trained encoder here, you get usually better results. And that's what we do. You just you initialize your encoder with some pre-trained network on different data sets, and you get better performance there. And we still do better than the baselines. It's in this side. Good. Now, that's fine. That was now looking at prediction, but we want to do molecular optimization. How does this method work now when you do molecular optimization? And the idea is that you are going to take now your neural network that has been trained on FSmol, and now we're going to use the encodings generated by this network that are optimized to put a Gaussian process on top of that. We're going to use now that for Bayesian optimization. And the way we do the Bayesian optimization is that we take the encoding of the molecules and then we train a Gaussian process on top of those encodings. And we show our method is here in red. Here we are minimizing, and we see that we do quite well in this problem. We want to find the optimal of the data is this value, and we want to find it as fast as we can. And we see that we do quite well in this setting. In this other, we do also quite well. Here we are maximizing. We have these two methods that are better than us, but we still do relatively well in this problem. And in this one, we do better than all the other methods. So these are problems that are different from the FSmol data. These are, for example, you try to optimize the docking score generated by some docking program on some data set. Antibiotic discovery, this is from the famous MIT paper by Regina Basili on antibiotic discovery with deep neural networks. I don't know if you have seen this paper. They use like graph neural networks to find new antibiotics. And we just do based off on the data set used for that paper, and we find the best molecule quite fast. Antiviral, this is a problem where you try to find, I think, some binding affinity to some COVID protein. And in material design, I think this is organic photovoltaic. You try to maximize the power conversion efficiency of organic photovoltaic. So that's great. We are able to obtain very good results in terms of Bayesian optimization. Here we compare with Gaussian processes on top of many different representations of molecules, like the fingerprints, then the molecular representation obtained by protonets and by many other different methods. And it seems that using this neural network that we have pre-trained on FSmol works really well in this case. We look also at the predictive performance in these out of distribution tasks, because they are not different like the FSmol problems, they are focused on binding affinity, and these are problems that are different. And you see that the predictive performance is already quite good with this problem. Good, so that's all. Some take-home messages. We have presented here this adaptive with kernel fitting with implicit function theorem. We call it, it has this fancy name. And this is a meta-learning method that combines deep neural networks and Gaussian processes for improved molecular prediction. You just train jointly your neural network and your Gaussian process model, and the neural network is specifically designed to maximize the predictive performance of the Gaussian process. It learns a feature representation that is optimal for making predictions with Gaussian processes. It achieves very good results on this small data set. Is the state of the art on this data set at the moment, and molecule net. And then we have seen that in Bayesian different problems, they work pretty well. So that's all. Any questions? I will be happy to answer if you have any.
I actually have one.
Yeah.
I have a couple of. So I think it's very smart the way that you do this sensitivity based, like pilot.
Yeah.
I was wondering if there is any relationship between using, for example, Gaussian mixtures and the classification and what you use Gaussian process.
Yeah, I mean, you could change your classifier. I mean, we're using this Gaussian process model. The prototypical network was using the nearest centroid. What you could do is other things, like for example, if you're doing classification, you could assume like a Gaussian for each class, and then you will get like a different classifier. I think the prototypical network doesn't get it, but I think you will get like a Fisher classifier. I think you just assume that the classes have like Gaussians with similar covariance metrics and different means, and you will get like a classifier, and that would be like another feature learning method. It will have a linear or quadratic decision bounding, and that will be maybe a restriction when you have more data, but maybe if it's small amounts of data, maybe it's fine.
I was wondering if there was any relation to the Gaussian process, just because of the nature of the Gaussian process, you know.
I mean, the motivation for using Gaussian processes here is because we want to get uncertainties and we want to base out conclusion. Probably if we wanted to solve other problems, maybe you could think of using other things. Maybe just a point of, I can mention a few things or a few lines that we are following to try to improve on this work. One of the key things, and maybe a limitation of this method, is that your neural network is fixed and it's the same across all tasks. And that might be fine in tasks where you have a small number of data points, because obviously you don't have enough data to fine-tune your network. And if you do that, you will probably overfit. And that's something that you don't want to do. One way to actually allow for tuning the network weights and avoiding overfitting is to, for example, use a prior on the weights of the network. And this prior could be shared across all tasks. And now for each task, instead of having a fixed value of the weights that is shared across all tasks, now you're going to take your prior and you're going to fine-tune your weights to optimize performance on your particular problem. If you don't have a lot of data points, your optimal network weights will be going to the mean of your prior. And that's going to prevent overfitting. And in tasks where you don't have a lot of data, the prior will regularize your network weights and avoid overfitting. But if you have a lot of data, the effect of the prior is going to be less. Your data is going to push more towards getting different weights of your network, and you will be able to fine-tune the weights of your network. And you will have now prior on your neural network weights that has been optimized for improving the predictive performance once you tune jointly your neural network and your Gaussian process model. And the prior has been optimized looking at performance on variation data. That's where the meta-learning thing takes place. So that's some work that I'm doing now with a postdoc in my group. We have obtained really good results on synthetic data, and we are now evaluating it on the small setting. My impression is that method should be better than this, because you can always take the method that the neural network weights from this method, you initialize the mean of your prior to that value, and then you just make a slightly large the variance. I mean, your prior is going to be Gaussian, which means, for example, whatever this method gives you, and then you just tune the variance. And then that allows you to control how much you want to deviate from the prior if necessary or not. And you tune the variance of your prior by optimizing performance on validation data. So you can control how much you want to deviate from that solution. My impression is that that should be for sure better than this.
And you apply Bayesian optimization on the model, right? On this classifier, right?
I mean, the classifier, we use the classifier was because in FSMOL, the problem is classification. And we want to see how well the Gaussian process does the classification problem, but for Bayesian optimization, we do regression. So, I mean, this whole framework works for classification or regression. And you just change the targets if they are discrete or continuous.
But I was wondering, so what you sample is your model base, not, let's say, not the experiment. Like you sample your whole neural network.
When you want to make predictions, or what do you mean by when you sample?
When you apply Bayesian optimization.
Okay, when we do Bayesian optimization, what we do is we take our molecules, we encode them using the learned neural network, and then we put a Gaussian process making prediction from those feature vectors encoding the molecules and the properties of the molecules. And now we use the predictions of that Gaussian process model to do Bayesian optimization. And the way we do Bayesian optimization is that you have a particular data set of molecules and you want to find fast the best molecules in that data set. So it's like based on a grid. We don't really do kind of design of the molecules on the fly. You just have like a grid of molecules and you want to find the best one fast. You could connect this with a method that generates molecules. And you could do fancy things like combining these methods with the generative models of molecules, for example. Good. Any other question? Yes.
So do you, I mean, like in the meta setting, basically started.
Yeah. This is deep kernel learning within a meta learning setting. In deep kernel learning, typically you only have like a training set. And then you just optimize performance on the training set, and you optimize jointly your Gaussian process model and your kernel. And that's why you overfit, because there is only like one task. And this thing is using these 5,000 tasks. And then it's very hard that you would overfit. I mean, what the overfitting happens because you would use your neural network, and imagine that you're solving a classification problem. And maybe the neural network is just separating your classes really well on your training data. And it seems that you get like a very simple classifier and the problem is very easy to solve. But then in new data, what happens is that the neural network is not going to separate the data so well. But this thing is using tons of tasks, and it's very hard that you find a neural network that kind of seems to work well on a task. I mean, that is going to work well on all these tasks. Maybe the other thing is that we optimize performance looking at validation data. And maybe that could also make a difference. I think that increases some robustness to overfitting as well.
I have one more. I don't know. Thanks for my question. I wonder, this space of molecule graphs, and you want to build this in code as such that being mapped in a way that things are like locally transferred, so things are similar in graph space, they're similar in Is there anything to say that you're going to have this continuous time?
I mean, people have to work a lot with molecules, and in practice, they have to expect that there is this connection between similarities in the structure of the molecule and the properties. But you have to be careful because chemical space is quite discontinuous, and there's something called this activity cliffs. And the reason, the activity cliffs is that you change slightly maybe something in your molecule. The molecules seem to be very similar, but the properties are extremely different. And you can have this in chemical space, and that's why you have to be careful when using machine learning. In practice, very simple methods like the polygraph fingerprint that is based on a kernel method of graphs. They work really well. And the reason for this is that typically you have this smoothness where similarities in the structure translate into similarities in properties, but sometimes this doesn't happen and you don't have this accuracy base, and that's why you have to be careful. Yeah, I think I would say in general, I mean, that's why people in chemistry apply machine learning because otherwise it wouldn't work. If you wouldn't have this thing that similarities in the structures translate into similarities in properties. Good. Thanks, Hal.
Thank you very much.